this last afternoon session of the conference. The first speaker will be Priyanka Mazumdar, and she will tell us about Arakelov self-intersection numbers on modular curves.
Okay, thank you for the introduction. I also like to thank the organizers for giving me this opportunity to speak here. So I'll talk about Arakelov self-intersection number on modular curves. So this is joint works with Anna von Pipich and Devargo Banerjee and Chitrabhanu Choudhury. So, so this is the outline of my talk. First, I'll give the introduction, then some preliminaries, and then main results. So for any positive integer n, let gamma be a level n congruent subgroup, and associated to gamma, we have a modular curve x gamma over some number field k. For example, if you take gamma naught of n, then this is one example of congruent subgroup of level n, and its associated modular curve is denoted by x naught n, and we consider the field to be a set of rational number. Okay, now I'll introduce the intersection numbers on arithmetic surfaces. So let Gn be the genus of the modular curve x naught n. For Gn greater than 1, there exists a minimal regular model chi naught n over z for the modular curve x naught n. So in other words, chi naught n is an arithmetic surface over spec z. That is, it's a scheme of dimension 2 with a proper flat morphism f, which is from chi naught n to spec z. So one can draw this following picture. So this is chi naught n, and this is my spec z. So for any prime p, let's this special fiber looks like this, and we can compactify this system by adding a point infinity, and over infinity we have the special fiber Riemann surface. Okay, so now for any two Hermitian line bundle L bar M bar on any arithmetic surface chi, Arakelov has defined a intersection number L dot bar dot M dot bar, which is a real number. Let omega chi naught n be the relative dualizing sheaf on chi naught n. Arakelov defined a metric on this dualizing sheaf, and Arakelov self-intersection number is this given by omega bar square chi naught n, which is where omega bar is this pair dualizing sheaf with this Arakelov metric. So we are interested in this quantity for the modular curve x naught n. So Arakelov self-intersection number of the relative dualizing sheaf can be written as summation over sigma geometric and plus sigma analytic, by which I mean this geometric part, this is a finite sum, and this is the analytic contribution. So the geometric part encodes the finite intersection of the divisors coming from the cusp 0 and infinity. And the analytic part is given in terms of canonical Green's function, which I denote G can 0 infinity. And this Green's function also sometimes people call Arakelov Green's function. So this intersection number omega bar chi naught n is independent of the number field k if the minimal regular model chi naught n is semi-stable over the ring of integer OK. So now some preliminaries. Let mu hype z be the 1-1 form corresponding to the hyperbolic metric on x naught of n. Locally, it is given by mu hype z. This is equal to I by 2 dz bar imaginary part of z square. So let this okay. So if you take if you integrate x naught n over this mu hype z, this is so-called the volume of gamma naught of n, or volume of the x naught n. So mu delta hype is my hyperbolic Laplacian on x naught n, and locally it is given by minus y square rho x square plus rho square plus 2y square, and this here z equal to x plus iy. So for any smooth function f on x naught n, you have this formula. Del, if you apply this Laplacian, hyperbolic Laplacian on any smooth function and multiply with this hyperbolic 1-1 form, you'll get back 4 by dz, dz f. Here dz and dzc are the two differential operator, dz equal to dou z plus dou z bar and dzc equal to dou z minus dou z bar minus 4 pi I. Okay, now I'll introduce the canonical Green's function. For that, I need the canonical 1-1 form. So 1-1 form corresponding to the canonical metric is given by this. Mu con z, this is equal to I by 2 by gn. Gn is a genus. And f mod of fz, f gz square, dz dz bar. Here f1 until fgn at the orthonormal basis of weight 2 cusp form with respect to the Peterson inner product. Okay. So now let G can be the canonical Green's function for the modular curve x naught n. So, previously I have given you the hyperbolic 1-1 form. With respect to the hyperbolic 1-1 form, we can also define this hyperbolic Green's function. And this Green's function have the logarithmic singularity along the diagonal, meaning G mu zw plus log of z minus w square, this is equal to big O of 1 as z goes to w. So here mu can be either mu hype or mu con. So and away from the diagonal, it is characterized by this following differential equation dz dzc g con zw plus delta wz equal to mu con z. Delta wz, this is the Dirac delta distribution. And it has a normalization condition, which says that if you integrate with respect to this 1-1 form, you'll get 0. Okay. So now some useful result. Let dm be the Arakelov divisor orthogonal. Dm be the Arakelov divisor corresponding to the cusp 0 and infinity, which are orthogonal to each Bm, where Bm are the linear combination of irreducible component of special fiber of the regular model chi naught n over Fp. Then the intersection product of dm is given by 2 into the degree of k over q and the rounded height of this line bundle ODM. So this is given in the Faulting's paper in 1984. So second useful result is in 1998, Michel and Unmo proved the following bound for the Nérontate height of this of such kind of dm. This is given by O of log n tau n square m for m0 infinity. So here, as I said, like we am considering k as the set of rational number and tau n is a divisor function. So these two are the useful theorem which we need to prove our theorem. First of all, we prove that dm, the Arakelov divisor corresponding to the cusp 0 and infinity, which is orthogonal to each V, which we prove that such dm is equal to k of chi naught n minus 2gn minus 2 hm plus Vm. So here m is 0 or infinity. This is the canonical divisor. Canonical divisor corresponding to this dualizing sheaf. And this is the horizontal divisor corresponding to the cusp 0 and infinity. And this is the vertical divisor corresponding to 0 and infinity. So first we prove this, and then using this Faulting's theorem, we prove the following identity. Chi naught of n omega naught of n omega chi naught of n square, this is equal to minus 2 genus gn minus 1 h naught h infinity, the intersection product of this, plus 1 by gn minus 1 Gn intersection product of V naught V infinity minus V naught square plus V infinity square by 2 plus this bound log n tau n square. So this is what we get for the Arakelov self-intersection number for the dualizing sheaf. So this part I call it this analytic part, and the rest of the part I call it the geometric part. So here again we also know that H0, H infinity, the horizontal divisor, is given by the Green's function. Okay, I think something. Yeah. Okay. So this is the first theorem we proved. This is a joint work with my PhD supervisor, Anavan Pipish. So here we prove that for if you take any positive integer n, then 2g 1 minus g, 2g 1 minus g can, this is equal to 2g log n plus little g log n as n goes to infinity. So as I said, the main motivation comes from this, because of this analytic part is exactly equal to this quantity. And in 1997, 1998, these are the two papers. One paper is in Abbes and Ulmo, this is 1997, and another paper is Michel Ulmo, this is 1998. They proved this this result for square free n, and later this was generalized by Banerjee, Bora, and Chitrabhanu for n equal to p square. Okay, so let me give you some outline of the proof. So for square free n, Abbes Ulmo, they use the following formula. So if you take two cusps k and l, then this canonical Green's function is equal to 4 pi ckl. This is the scattering constant with respect to cusp k and l, 4 pi divided by volume plus limit s goes to 1 integration over x cross x g s z w. This is automorphic Green's function. Mu can z, mu can w. Okay, s into s minus 1 by volume and minus 4 pi limit s goes to 1 integration of the Eisenstein series with respect to k zs mu can z plus integration of el w s mu can w minus 2 by s minus 1 by volume. So this is the formula they have used to prove this asymptotics. So for if n is not square free, this part, this third term gets quite complicated. So we in our theorem we haven't used this formula. So we have used the hyperbolic heat kernel approach, and we prove that if you take two Green's function, hyperbolic Green's function and the canonical Green's function, the difference is given by Ez plus EW. Okay, so where phi z is equal to integration 1 by 2g, and one more thing, this formula is true for any finite index subgroup, and KL can be any cusp. And this formula is also true for any finite index subgroup. And here my ZW can be Z not equal to W, but ZW can be anywhere in X naught n. Okay. 2G gamma G hype Z zeta F of zeta mu hype zeta minus 1 by 8 G gamma square integration x cross x G hype zeta, eta, f, eta, f, zeta, mu hype, eta, mu hype, zeta. So we have used this formula for to prove this theorem, and so this using hyperbolic heat kernel, this approach was originated. Okay, so I have mentioned what is f zeta. So f zeta, this is equal to 0 to infinity, the hyperbolic Laplacian hype zeta t, acting on the hyperbolic heat kernel a hype t zeta dt. So this was originated from Jorgensen and Kramer, and then later this was generalized by Narasimha. So yeah, so we are using that theorem to prove to get this asymptotics. Okay, maybe the last step. Okay, so using that formula, we get 2gn, 1 minus gn, g can 0 infinity. This is again for gamma naught of n. This is equal to 8 pi gn, 1 minus gn, c 0 infinity. This is the scattering constant with respect to cusp 0 infinity plus little g log n as n goes to infinity. Now from the literature, we have the explicit expression of this scattering constant, and from there it's direct to this asymptotics. Okay, so this is the theorem 1. So then the second theorem, this is joint work with Devargo Banerjee and Chitrabhanu Chaudhary. So here we prove for any prime p and r is 3 or 4, the Arakelov self-intersection number omega bar square chi naught p power r, this is equal to 2g p power r log p power r plus little g p power r log p as p goes to infinity. So here chi naught p power r is a minimal regular model for x naught for the modular curve x naught p power r over q. So okay, so now the main ingredients for this is one of the paper by Erikson, which appears in 1990. He has given explicit description of the regular model for x naught n, and the special fiber of the regular model, it depends on the parity of p. So this so p can be 1 mod 12, 5 mod 12, 7 mod 12, and 11 mod 12. Okay, so some outline of the proof. So by using this Fording-Liljak theorem, we get this identity, which I have, I think, also mentioned somewhere here. So yeah, so using this theorem, we get this formula. Then okay, so then we explicitly compute the Vm, which is appearing here, V0 and V infinity, which are the linear combination of the all irreducible component of the special fiber of the minimal regular model. And then we prove this asymptotics, that this part is equal to g p power r, little g p power r log p as p goes to infinity. So together with the analytic contribution, we get the omega bar square x naught chi naught p power r is 3 g p power r plus little g p power r log p as p goes to infinity. Okay, so now some outline how we prove this. Okay, so this is the special, as I said, the special fibers of the of this minimal regular model is explicitly given by Erikson. So for r equal to 3, so p x naught p power 3, it's given by this. So first picture is for p equal to 1 mod 12, second is for 5 mod 12, then the third is 7 mod 12, and the last is 11 mod 12. And if you take r equal to 4, this special fiber looks like this. So yeah, so for each cases, we have to find the intersection matrix for this special fiber. So we calculate the intersection matrix for the special fiber of the regular model. I will give one example. So so this is the easiest, the smallest, small looking example. That's why it's written down. So Okay, so let me draw the picture for this case. So this is a special fiber in this case when R equal to 4 and P congruent to 11 mod 4. So C, this is C40, this is 31, C22, C13 and C04, and this is E and F. And this is the intersection matrix which we calculate. And if you notice in the matrix C22, this square is equal to -1. So that means it is an exceptional divisor. So in this case, this model is not minimal. So we need to blow downs. After 3 successive blow downs, we obtain the minimal regular model. There, the intersection matrix, we don't have this -1. The final intersection matrix looks like this. So from here, we calculate this. We calculate this BM, which are the linear combination of these 4 components, and we prove okay. Yeah, and we prove this formula. So yeah, that's all I have to say. Thank you.
Thank you for your talk, Priyanka. So are there any questions? This title? Yeah, so I mean, not direct application, but there's a notion of faulting site. So, so Euler's formula tells us that faulting site of the Jacobian J naught of n, this is exactly equal to omega bar square x naught n plus something. But here x naught n has to be semi-stable. Semi-stable over this ring of integer. Okay, but in our case for p cube and p to the power 4, it's not semi-stable. So first we have to find out the semi-stable model, then we have to calculate this, then there's application. So and for in square free, this model, this model is semi-stable. Semi-stable over Z. So for square free n, they can directly use this asymptotic formula. Yes, yeah, so I should mention that also. So there is recently this work is generalized for any n. So there are 2 mathematicians. I don't know how to pronounce, but Dolce maybe and Mercury. So this appears in June 2023 archive. So they have generalized this result and for any n. So yeah, and we have put it our result on archive. Just our result was there from October 2020. So yeah, so after some time they could run the whole algorithm for any n. Any n. Yeah. So, but yeah, long computations and all.
So we have explicitly written down. For example, if you see the intersection matrix, I mean, they have not given the explicit intersection matrix, but yeah, for at the end of the day, I don't think you need the intersection matrix. You just need this this formula. So they have proved this. Yes. I don't know.
So I have a related question. So you just said maybe you don't need the intersection matrix. In that case, would it be possible to extend these results to other families of modular curves?
You mean for x1 and xn?
For example?
Yeah. There are results also in those directions. So there is like PhD students of Jürg Kramer, Meyer, Hartwig Meyer. So he has proved this the same thing. He has proved the intersection self-intersection number of the realizing sheaf for x1n for n square free. And from that, he could also derive this faulting site. But yeah, for x1n, and another student of Kramer, Rados, he has considered the modular curve xn and also n square free. But in this case, his model is not semi-stable, so he could not go to the faulting site. Not semi-stable.
No more questions. Let's thank the speaker again.